In this work, we scale up constraint learning from demonstrations using Gaussian processes. We are given demonstrations of a system, like a quadrotor, which satisfy a complex unknown constraint, like a non-convex obstacle. We visualize such a case on the left, with demonstrations in black and an unknown constraint in blue. We want to learn the unknown constraint from the demonstrations while making minimal structural assumptions, and to use the uncertainty in the learned constraint to plan new trajectories which are constraint satisfying with some probability. To set things up, we are given demonstrations which are locally optimal solutions of a constrained optimal control problem. We know the demonstrator's cost function and some of the constraints, and we want to learn a complex unknown constraint, G unknown, which has unknown functional form and offset. One toy example in this setting is learning an unknown ellipse obstacle from path length optimal demonstrations. Since the demonstrations are locally optimal, they must satisfy their KKT optimality conditions. These include primal feasibility, ensuring the demonstrations are safe, complementary slackness for the inequality constraints, ensuring Lagrange multipliers are zero unless the constraint is tight, and stationarity, ensuring the demonstration cannot be locally improved. To find the unknown constraint, we can solve an inverse KKT problem, which recovers the constraint that makes a demonstration's KKT consistent. This problem is challenging to solve, so we solve it approximately via tractable subproblems. We first identify in problem 2 where the demonstrations must be on the boundary of the unknown constraint by zeroing out the unknown constraint in the inverse KKT problem altogether. We can then deduce that the unknown constraint must be tight at time steps where stationarity cannot be driven to zero without the presence of the unknown constraint. We can then solve problem 3 to find a consistent set of gradients for the unknown constraint at the type points by fixing the Lagrange multipliers of the unknown constraint to be 0 at non-type points and a non-zero value, like 1, at the type points. This information can invalidate many other possible gradients. Then, our core insight is that the KKT-derived information on the constraint values and gradients can be directly incorporated into a Gaussian process, which are flexible function approximators that require minimal a priori knowledge on the underlying constraint. Since the derivative of a GP is also a GP, training a GP using the constraint value and gradient data is straightforward. Incorporating both the constraint value and gradient information is crucial for accurate constraint recovery with reasonable posterior uncertainties. Finally, given the trained GP, we can evaluate the probability of a candidate state being safe with respect to some confidence interval, and use this to compute probabilistically safe plans by using Boole's inequality to bound the overall probability that the entire plan trajectory is safe. We evaluate our approach on a 12D quadrotor. We are given 13 demonstrations avoiding a non-convex obstacle to be learned, and we assume no prior knowledge on its structure. Our method recovers a constraint which is highly faithful to the ground truth obstacle with minimal classification errors. Moreover, due to this accuracy, using our planner to compute plans which are safe with probability 0.9 returns plans that are safe for the true constraint. These plans are visualized in gold on the left. In contrast, previous constraint learning methods, which approximate unknown constraints as unions of boxes, fail to accurately recover the constraint. We conclude with a summary of our work. Thanks for your attention.